Okay, hello guys, this is P3 integration. So again, I have the textbook right next to me. I am teaching exactly as the textbook goes and what you need for the specification. So integration starts with, just like differentiation, it starts with some known definitions, some known integrals that are standard. So yes, let's jump right into it. This in the textbook, it's called integrating standard functions. Standard functions, because their integrals are very standard. They are known and defined through ages. So okay, integral of x raised to n dx is okay, this one, add 1 to the power, divide by the new power. This is the basic most integral of an x term raised to any power. So add 1 to the power, x raised to n plus 1, divide by the new power, plus c. So let's say if it's x raised to 4, integral of this would be x raised to 5, add 1 to the power, and then divide by the new power, plus c. So this is the first most. I think you know all this from P1 or P2. So that is the first one. And then the second one comes from, okay, the second one has a link to differentiation. The integral of e raised to x is e raised to x again, plus c. Because remember, integration is the opposite of differentiation. It's doing the opposite of what you do when you're differentiating. So yeah, integration is the antithesis of differentiation. When you differentiate and then you integrate, you should get the same function back. But then the thing is, integration is not as simple as differentiation. For differentiation, there's a set of very key and useful rules that you can use and differentiate any function, no matter how complex it is. Chain rule, product rule, and quotient rule can be used in combination to very complex functions and you can differentiate. But the thing for integration is there's no such basic rules that work all the time. For integration, integration is known to be more difficult than differentiation, because differentiation is basics. Once you know the rules, you can do it. But integration, yeah, there are rules, but they don't apply all the time, so you have to be careful. For integration, the most important thing is you're getting the antiderivative. That means after differentiating, for integrating, the key thing is getting the antiderivative. So after integrating, see that if you differentiate this term on the right hand side, you get back the integrand. So let's whatever some terminologies. In something like this term is called the integrand, the thing you are integrating with respect to x. And this is the integral. It's the answer you get after integrating. So this is the integral, this is the integrand. So in that way, whenever you integrate and you get an answer, try differentiating this using the basic rules we have learned. Differentiation will always be easy because of the rules we have learned. Differentiation will never be a challenge once you've mastered the said rules. So once you've integrated, try differentiating this and see if you get this exact back. If you do, your integration is correct. Otherwise, it might not. Otherwise, it's not actually. By definition, an antiderivative, which is the same as an integral, an antiderivative when differentiated should give back the original term or the original polynomial. So yeah, for integration, the key thing is try differentiating once you've integrated and see if you get the original answer. That's the only way you can know if you're correct, because integration is complicated. It doesn't have the key basic rules that work all the time, so you really have to be careful. So in such a case, you can see why this is correct. Number 2, this standard definition is correct because obviously we learned that the derivative of ex is ex. So the integral must also be the same, because what I said, that proof holds. When we differentiate this, we get this back, hence this integral must be correct. So using that same logic, we integrate 1 over x dx. Remember, in differentiation, we said the derivative of ln x is 1 over x. So in integration, the integral of 1 over x must be this, so that when we differentiate this back, we get the same thing back. Hence, we know this integral must be correct. And then this modulus sign comes because sometimes when you plug in limits, say you have a graph, of 1 over x, 1 over x looks like this, and you want to find the area in this side of the region where x is negative. Let's say you want to find that area. So when you will integrate, you'll get 1 over when you integrate 1 over x, you'll get ln of x, and then when you plug in these limits of negative to find the area, that's how we do the area. We would put in limits here and here, and then we would put in limits here and here. If we had negative answers, then you couldn't evaluate the logarithm of it. Hence, we do the modulus of it. So we ignore the negative signs basically. So if it's ln of, let's say we're trying to find the area of this graph 1 over x. This graph is 1 over x from -2 to -1. -2 to -1. So in that case, the c goes, because now it's a definite integral, from -2 to -1. Now, if you didn't have the modulus sign, you couldn't do the logarithm. But now that we have it, and that's why we have it, instead of -1, you would just put 1. So ln of 1 minus ln of 2, because the -2 becomes 2 in the modulus sign. So that's why the modulus sign and the fact that the derivative of this is this makes sense that this is true, because again, the fundamental of integration is ensuring that the answer you get when you differentiate it, you get back the integrand. Okay, number 4, basic definition, cosine x dx, integral of cosine x dx. Now again here, basic definitions from differentiation comes. The derivative of what gives cosine. When you differentiate what, do you get cosine x? The answer is sine x. So the integral of cosine x must be sine x plus c. Because when you differentiate this, remember sine x will give cosine x, and then the c is a constant. So in differentiation, that becomes a 0. Hence, when you differentiate sine x, you get cosine x, and this is true. Number 5, integral of sine x dx. Now, when you differentiate what, do you get sine x? Remember, it's not just cosine x, it's negative cosine x. Because the differential of cosine x is negative sign. So if we want a positive sign here, we must negate this. So the answer is this: the derivative of sine x is negative cosine x. And one other thing about integration sign and the integral sign in general, it is that you can move constants, and let's say a negative sign like this, because the negative sign is basically just -1. So you can move it through the integral sign. Let's say you have integral of negative sine x. It's the same as in negative integral of sine of x. So this is a very useful thing when you will encounter difficult integration problems. It's easy to remove constants outside because they mess up your work and can lead to mistakes. So you remove constants and negative signs outside so that you're left with just basic functions inside. So an example of that, let's say you have an integral of 4 e raised to x plus 4 sine of x. You could just remove the 4 outside at once. So you get 4 integral of ex plus sine x. You can remove the 4 so that now this is much easier. With the 4's here, it could lead to mistakes. So again, you remove the 4's. If there is a negative, let's say it was a -4 here and a negative, you could remove the negative also so that now it's both positives. And another key thing, this is actually P4, but it's very important to remember it. A negative, let's say whatever we have here, any integral, a negative will switch the limits. If it's a definite integral, now it becomes from b to a. You see how it's from a to b, but then there's a negative sign outside the integral. That negative sign, when you make it positive, you switch the limits. So now it's not from a to b, it's from b to a. And then the integral remains the same. So this is also a key thing. Remember that. That'll actually come in P4, but just so you know. Okay, and then the standard definitions keep going on, but then these other ones are, okay, they're not that hard. Okay. Number 6, integral of sec squared x dx. Now remember, in the differentiation video, I proved that the derivative of tan is sec squared. So the integral of sec squared must be tan x plus c. That's just it. And then 7. Integral of cosec x cot x is negative cosec x plus c. Now this, you can ensure that this is true by yourself. Try differentiating negative cosec of x, which is just negative 1 over sine x. Use quotient rule to differentiate this. You will get this, and so you will know that this is true. 8. Integral of cosec squared x dx is negative cot x plus c. Again, try differentiating negative cot x using quotient rule. You will see that this is true, hence yeah. And then the last one in the textbook is sec x tan x. The integral of sec x tan x multiplied is the same as sec x plus c. So these 4, don't worry about these 4, they are given in the formula booklet. You don't need to remember this. So that, let's say in a question you're supposed to integrate something like this. If you don't remember it, it's in the formula booklet. So that one term, if let's say you're supposed to integrate a long chain of terms and one of the term is sec squared, you automatically know that its derivative is tan and all these other terms. So when you see this, don't be scared. These are just basic integrals that are defined and they're in the formula booklet. So these 4, try to prove them on your own by differentiating this using quotient. This one we already did. Try differentiating this to get this. That way you'll know it's true, and then it'll be given in the formula booklet. So don't worry. All you need to know is the ones for sine x, cosine x, 1 over x, ex, and the normal one, x raised to n. So that's it for standard definitions in the booklet. These are very key like if you don't know these, you can't do a question. These are the fundamentals. You need to know the fundamentals very well. So let's see some examples in the textbook. Integral of 2 cos x plus 3 over x minus root x dx. So the integral sign is such that, well, you can integrate each term separately because it's distributive. You can distribute the integral sign to all these terms. So okay, you don't need to do this, but I'm just showing something, a fact about the integral sign. Again, you know how we said we can remove out the constant, so you can move out the 2 outside, plus 3 integral 1 over x minus integral of root x is the same as x raised to half. And then obviously all these places we need dx, otherwise it doesn't make sense. So all I'm saying is that these 2 are equivalent. The integral sign is distributive. You can distribute it across all the terms as long as they're separated by a plus or minus sign, because it's an addition, not when it's a multiplication. When it's addition, you can distribute it among these, like opening brackets. You integrate each term, and then, as I said, you can remove out constants, which makes your work easier. This 2, I removed it so that we get 2 integral cosine x plus 3 integral 1 over x, because I factorized out the 3 so that now it's outside the integral sign. And then the minus sign, I also didn't put it here, I removed it outside, minus integral x raised to half dx. And then now this becomes much easier. The integral of cosine, we know it's just sine, so it becomes 2 sine x, the 2 and then times the integral of this, so 2 sine x plus 3 ln of x. Again, this is from standard definition, and then this is the first standard definition, add 1 to the power, divide by the new power. So x, add 1 to 3 half, we get 3 over 2, and then dividing this by 3 over 2 gives us 2, like that. So yeah, the final answer is exactly this, plus c. Don't forget the plus c, because it's an indefinite integral. That's question A. Let's see B. B is the integral of cosine x over sine squared x minus 2 e raised to x. Now you will see that this term is very hard to integrate, but now you have to use some trigonometry. You can say that cosine x over sine squared is the same as cosine x over sine x times 1 over sine x, because this is equivalent to this, which gives us cot x cosec x. And then remember from an earlier definition I gave you, the integral of cosec cot, because remember now this integral simplifies to, because this term is the same as this, so cot x cosec x minus 2 e raised to x dx. Now again the integral sign is distributive, so you integrate each term separately. From a definition I gave you, the integral of cot cosec is negative cosec, so this becomes negative cosec x, and then yeah, because this is e raised to x, it remains the same, plus c. This is the integral. There you go. So that's it for standard definitions and all examples of standard definitions. Now we go to a very basic application of reverse chain rule. So the textbook says, it's topic number 7.2, it says integrating f of ax plus b. So what does this mean? It means this is a composite function. Firstly, the outside function is f and the inside function is ax plus b. So this is a very okay, you'll get to know what I'm talking about, but then the outside function is f and the inside function is ax plus b. So it's really easy to integrate this by kind of reversing the chain rule of differentiation. You know how chain rule we used composite functions like this, outside function, inside function. So integrating this, you kind of reverse it in a way that you'll understand. But okay, there's a key thing, but I'll come to it later. So for example, cosine 2x plus 3, integral of this. So for this, you kind of use a reverse chain rule for not kind of, you do use a reverse chain rule of differentiation. So the answer is, first of all, you differentiate the outside function, integrate, sorry. First of all, you integrate the outside function, cosine, which becomes sine, and then the inside function remains the same, remember? And then divide it by the derivative of the inside function. In differentiation chain rule, we were multiplying the derivative of inside function. In integration, we divide by the derivative of the inside function, and the derivative of the inside function is just 2 plus c. So you integrate outside function to get sine, the inside function remains the same, and then you divide by the derivative of inside function. Remember, you divide by the derivative of inside function. You differentiate this to get 2 and then divide by that, and then this is now the answer of the integration. So it can be very confusing, but then why this works is the same reason. Try differentiating this. Try differentiating half sine of 2x plus 3, which is exactly this. So when we differentiate this, we will get the outside function. The outside function of sine becomes cosine. The inside remains the same, 2x plus 3, and then the derivative of the inside times this, because that's a coefficient. Remember, what I'm doing here is differentiating this to show that it gives back this, to show that the integral is correct. So in differentiation, we will multiply by the derivative of the inside. So we get 2 times 1 over 2, which gives just 1. And then the c goes, because differentiating a constant becomes 0. So differentiating this answer of ours gave us this back as we wanted. Hence the integral is correct. So that is a key and very basic application of reverse chain rule. So example 2, e raised to 4x plus 1, integral of this. The outside function is e, the inside function is 4x plus 1. So 4x plus 1 is in this case this term. So when we integrate this, we get the outside function remains the same, and then you divide by the derivative of the inside function, 4 plus c. The outside function remains the same because the integral of e raised to x is e raised to x. So e raised to this will also become that, Yes, and then part C, let's say we have integral of sec squared 3x dx. Remember, we already said that the integral of sec squared in general is tan x. So this becomes tan 3x, divided by 3 plus c. Because the outside function integrated becomes tan, the inside remains the same, and then you divide by the derivative of the inside, which is 3 plus c. So now a key thing about this is, let me clarify this. For this rule and for P3 in general, this term, this thing you see here, ax plus b, a function of ax plus b, this ax plus b must be linear. By linear, I mean it's the highest power of x is 1. So as in all the examples we did, 4x plus 1, cosine of 2x plus 3, and then sec squared of 3x. So in all those examples, we found that the power of x is just 1. So it's linear. It's not quadratic where we would have ax squared or cubic, ax cubed. It's linear. It has to be linear. Don't generalize this rule because, as I said, integration is complex. If, let's say, we had integral of 4x squared plus 1, you can't say that you integrate the outside function giving this and then you divide by the derivative of the inside, which is 8x. This is not correct. This is not correct. Try differentiating this. You will not get back this. So this works only when this thing inside here is linear. That's only when you integrate outside function, leaving the inside the same, and then you divide by the derivative of the inside. So in this case, the derivative of the inside will always be a, which is a constant. That's what we want. We never want to divide when the derivative itself has x. Like in this case, 4x squared, we differentiated, we got 8x. Whenever you have such a case, this has to be linear. If it's quadratic, this rule of outside and then divide by derivative of inside doesn't work. This is incorrect because when you try differentiating this, you will not get back this. So that's very key. Don't forget that. Always, and for P3, you will never be expected to do something like this. It will always be when this is linear, so that its derivative is a constant 4 and you can divide by it without any worry. So in P3, don't worry about anything more complex. F of a raised to x at any power n where n is greater than 1 will not be tested. The power will always be 1. It won't be 2 or 3 or 4, because when it becomes more than 1, the rules change and you can't use this anymore. So again, just to emphasize this, because it's confusing, in P4 you'll have to encounter something like this, but yeah, and that's when you'll now learn more complex tools to integrate, techniques, because as I said, integration is much harder than differentiation, and the techniques that don't work for everything. You have to see which one works where. So unlike in differentiation where the general rules work all the time. So in this case, you can't say sine of 2x squared plus 3 divided by the integral of the inside function 4x. No, this is not correct. This is not correct. You can't divide by 4x because 4x is the derivative of the inside function. It has to be linear. The inside function has to be linear. So that's it for a very easy application of reversing the chain rule. For P3, don't worry, it'll all be linear questions. It will never be anything more complicated than that. So in general, the textbook says, in general, the integral of f prime of ax plus b becomes f of ax plus b divided by a plus c. So you see that, don't you? When you integrate f prime, you get f, no shit, and then ax plus b, it remains because it's the inside function, divide by a. We want it, and it will always be just a constant, because this is linear, plus c. So there we go. And that's it for reverse chain rule. Very key, very basic thing. So another example, the textbook has these examples. Let's see. The integral of 1 over 3x plus 2. So here we say that the outside function is 1 over something. That is itself an outside function. And the inside function is 3x plus 2. So the integral of this should be as we know, when it's 1 over something, when this is linear, we use ln. So yeah, ln of 3x plus 2 modulus sign, remember, over 3 plus c rather. So because it's linear, remember, it'll always be linear for P3. Don't worry about anything harder than that. 1 over this gives ln of this over 3. Now try differentiating this and you will see that you get exactly this back. 1 over 3 ln of 3x plus 2. When we differentiate this, we get exactly this back. Now it should be very easy to see this. So it's true, yeah. Another example textbook has 2x plus 3 all raised to 4. Now the outside function is the fact that it's raised to 4 and the inside function is 2x plus 3. So to integrate this, we add 1 to the power to the whole brackets, add 1 to the power, divide by the new power, and then divide by the derivative of the inside function, which is 2, so put it in the denominator. So we get 1 over 10 2x plus 3 all raised to 5 plus c. Exactly. So there we go.